Okay, everyone. Today's lecture is Chapter 9, the second lecture of Chapter 9. So let's go to page 48. Here is page 48. So we studied the hypothesis test, and today so I will discuss the hypothesis test based on the examples. So our hypothesis test is so focus on the testing mean. Okay? So if you have sample mean, then this sample mean is meaningful value or not. So that is the testing for a mean. So we have two cases. So we will first explain the population mean mu, test for the population mean mu. And so we have a sampling distribution for x bar, depends on whether or not the population variation sigma is known. Okay. So we have two cases. One is so population variance sigma square is given, so known population variance. Or if we don't know the population variance, then we have to use another way. So this example, we assume that we know the population variance. Okay? So we've studied at chapter 8, also two cases. One case was that we know the population mean, and another case was that we don't know the population variance, I'm sorry. So we have two cases. First, population standard deviation or population variance is known, or so population standard deviation is unknown. So when we study the confidence interval at chapter 8, population standard deviation is known, then we used the normal distribution. And if population standard deviation or population variance is unknown, then we used the student t distribution. So in this hypothesis test, we have the same technique as we did in the confidence interval. Okay, so first, let's assume that we know the population variance and check the examples. So we will we need a test statistic. So and if this test statistic is so not extreme, if this number is not extreme, then we can accept the null hypothesis. And this test statistic is so extreme, then we reject the null hypothesis. Of course, we need a benchmark mean mu 0 when we calculate the test statistic. Okay. And so because we know the population standard deviation or population variance, so we can use the z statistic, and we can assume that this z statistic is follow the normal distribution. Okay. Our z statistic is this value. So sample mean is obtained by the calculating sample mean using the collected data samples. And we don't know where is population mean, but we have benchmark mean for this x bar. So that is our benchmark, and that is our market standard. That is our specification. And here is the standard deviation, standard error for the sample mean, and this standard error is given by this simplification, sigma over square root n, sigma over square root n. So that's why we need population standard deviation. So sigma over square root n is sigma x bar. Okay, and so we put this number as a denominator, and we put the sample mean here and benchmark mean here, and that is t statistic. I will call it at z statistic. I will call it at zcalc or z statistic. So that is our test statistic. So this test statistic is in here between these two critical numbers. Then we cannot reject the null hypothesis in two-tailed test. And if this z statistic is located in here or here, then we reject the null hypothesis when we have the two-tailed test. Okay. Or if we are considering the right-tailed test, if z statistic or zcalc value is located in this area, then we do not accept the null hypothesis. Do not reject the null hypothesis. I'm sorry. We do not reject the null hypothesis. So the null hypothesis is not rejected. But this z statistic is located in this right-tailed area. Then we reject the null hypothesis. Left-tailed test case, if z statistic is located in here, this area, then we do not reject the null hypothesis. The null hypothesis is not rejected. But if z statistic is located in this left tail part, then our null hypothesis will be rejected. Okay? So that is the idea. So then, where is this value? We say that where is this value, this value, this value, and this value? We say that this value is critical point. These values are named critical point. So critical value or critical point. So critical value. So these critical values are different from the level of significance and the type of test: left-tailed test, two-tailed test, right-tailed test. This critical value is minus 1.282 if our level of significance is 10%. Level of significance is alpha. So alpha is 0.10, and if we are doing the left-tailed test, then this critical value is minus 1.282. Or if we are doing the right-tailed test and our level of significance is 10%, then the critical value is 1.282 plus, in this case plus, right-tailed test plus left-tailed test minus. And two-tailed test is different. If we are doing the two-tailed test, then the critical value, so in two-tailed test we have two critical values, is plus 1.645 and minus 1.645. So if this z statistic is located between minus 1.645 and plus 1.645, then the null hypothesis is not rejected at the level of significance 10%. Okay? So if your level of significance is 5%, if the level of significance is 5%, then then the critical value of left-tailed test is minus 1.645, and the level of significance, so the critical value for the right-tailed test is plus 1.645, and the critical point for the two-tailed test is plus minus 1.960. So minus 1.960 to from minus 1.960 to plus 1.960. That is critical point. And your level of significance is 1%, then left-tailed test the critical point is minus 2.326. Right-tailed test significant critical point is 2.326 plus 2.326, and the two-tailed test has the critical value plus minus 2.576. So these critical values so make the probability that the probability that our z statistic is less than minus 1.282. So this number is 10%. So that means the probability that our test statistic is less than minus 1.282 is 10%. So that's why it says that here is alpha. Okay? And on the other hand, probability that our t statistic is greater than 1.282 is also 10% here. And probability that our z statistic is between minus 1.645 and plus 1.645 is 90%, 0.90. That means the probability that z statistic is less than minus 1.645 or z statistic is greater than 1.645. So the z statistic is located in this area or this area. Probability that the z-calc is located in this area, left tail or right tail. So this probability is this probability is 1 minus probability that z statistic is between minus 1.645 and plus 1.645. So that is, I told you that this probability is 90%, so 1 minus 0.90, so that is 0.10. So the probability that our test statistic is located in this left tail area or located in the right tail area is 0.10, 10%. Okay? So it is the same if we change this number to this number to minus 1.645, then probability becomes 0.05. So it is the level of significance is 5%. If it is 1.645, then it is 0.05, 5%. And the probability that our test statistic is between, minus 1.645, less than minus 1.645, or greater than 1.645 is 1 minus probability that z statistic is between minus 1.645 and plus 1.645. So finally we have 1 minus 0.95, and we obtain the 0.05. So these numbers has that meaning. I'm sorry. So I will again. So it is. I've repeated the same thing. I'm sorry. So if this z statistic is between less than minus 1.960 and z statistic is greater than 1.960, is that 1 minus so 1.960 and 1.96. So probability that z statistic is between minus 1.96 and 1.96 is 1 minus 0.95, and we obtain the 0.05, 5%. So these numbers comes from these probabilities. Okay. So for example, let's study the example and understand what I talk about. And one company produced a paper, so for the razor printer, and the standard paper width is 2.216 millimeter, so 8.5 inches. Okay, and so the actual width of this random variable is normally distributed with the known standard deviation 0.0230. Okay, so that is important. We know the standard deviation. Okay. So and we collecting the sample papers from this produce machine, and we choose 50 sheets at random and measure them with a precise instrument, and the mean of width for this 50 individual papers are 216.0070. Okay? The mean of randomly selected papers width is 216.0070, and using a 5% level of significance, so that is alpha is 5%. The problem is, does this sample show that the product mean exceed the specification? So our paper producing this system works well. So we produce the papers, razor printer papers, and this width should be 216, but the randomly selected 50 papers, the width are not exactly same as 216, but it has an error. But we submit the sample 50 samples, width of 50 sample papers, and then we obtain that it is 216.0070. And standard deviation, sample standard deviation was 0.0230. So then, so this product mean exceed the specification. That is the problem. So then the question is indicates the right-tailed test because we say that it is exceed the specification. Our specification is 216 millimeter. So our null hypothesis is the mu population mean is less than 216 millimeter. And the alternative hypothesis is that mu is greater than 216 millimeter. Okay? It is, as I told, so it is right-tailed test. Okay? And our benchmark mean is 216 millimeter. That is step 1. State the hypothesis, null hypothesis. It is, we have to decide that right-tailed, whether this question is right-tailed test or two-tailed test or so left-tailed test. We specify that this is the right-tailed test, and our null hypothesis is that, and our alternative hypothesis is like that. Step 2 is specify the decision rule. Specify the decision rule. We says that in this example, we says that 5% level of significance. So here we say that alpha is 0.05. It is 5% significance level. Okay. So if we calculate, so our z statistic is when after we calculate the z statistic, and this z statistic is located in this area less than 1.65, then we do not reject the null hypothesis. But if this z statistic is located in the right tail area, and this area size is 0.05, 5% area, then we reject this null hypothesis. Okay? So this critical value is 1.645. This critical value is 1.645, as we discussed in this table 9.2. We say that it is 1.645. Okay? So we reject this null hypothesis if our test statistic z statistic is greater than 1.645. Otherwise, we do not reject this null hypothesis, as we discussed in this figure. So in step 3, calculate the sample data and calculate the test statistic. So the test statistic is given by this equation as we studied in the previous slide. So our test statistic is z as x bar minus mu 0 divided by sigma divided by square root n. So our sample mean is 216.0070. That is our x bar. And our benchmark mean is 216.0000. It is our benchmark value, and the sample standard population standard deviation was given as 0.0230. This sigma given standard deviation, population standard deviation. Okay, and the number of sample is 50. So we collect these 50 samples and calculate this x bar using these 50 samples. So number of sample is 50 and take the square root. After we calculate this equation, we obtain that 2.152. 2.152. So then we say that in here, so we reject this null hypothesis if this test statistic is greater than 1.645, and we obtain the 2.152. So the test statistic here is 1.645. It is critical value. And our test statistic is located the point at 2.152. So we reject the null hypothesis, okay, and we select the alternative hypothesis. Conclude that alternative hypothesis. So population mean mu is less than 2.16 is the null hypothesis, and this null hypothesis is rejected. And this alternative hypothesis, we conclude that this alternative hypothesis at 5% level of significance, 5% level of significance, okay? So that is the make a decision. So that means, so this producing paper process have some problem. So if we continue this, we produce this paper, this laser printer paper using this process, then the paper width is always larger than our benchmark so value 216 millimeter. So that is the conclusion. So we have to change the machine or producing process, manufacturing process, or something like that. So we need more accurate way to produce this paper. Otherwise, our paper is always greater than 216 millimeter. Okay, so that is the take action. So we've used the critical value. We used the critical value 1.645 to make a decision. But there is another way to make a decision, p-value method. P-value method. P-value method is more flexible approach and more convenient than the critical value method. So the p-value answers the following question. If the null hypothesis is true, what is the probability that we would observe our particular sample mean? Okay. So the answer of this question is p-value. Okay. So if this p-value is smaller than alpha, then the null hypothesis is rejected. Okay. So for a right-tailed test, the p-value is calculated by this equation. The p-value for the right-tailed test is probability that z is greater than z calc, where this z is standard normal distribution. So this z is standard normal distribution. So p-value for the right-tailed test is this, obtained by this equation. Okay? And this p-value is less than alpha, then we reject the null hypothesis. Otherwise, we fail to reject this null hypothesis. Okay? So p-value is, again, the probability of obtaining a test statistic as extreme as the one observed. Okay? So that is p-value. The large p-value is good news, and the small p-value is bad news. Okay? If this p-value is less than alpha, then we reject the null hypothesis. So the p-value for the right tail test is, in this example, the paper, so laser printer paper example, is the right-tailed test. So p-value for the right-tailed test, p-value for the right-tailed test is probability that z is greater than z calc. And in this example, the z statistic is 2.1152, so p-value is obtained by this equation. So right-tailed test. So then, if we have the left-tailed test, then p-value is that obtained by probability that z is less than z statistic, where in both of this equation, large z is the standard normal distributed random variable. So if this p-value is less than 5%, then we reject this null hypothesis and select the alternative hypothesis as the conclusion. So to calculate this number, this p-value, we can use the Excel function. So then using the Excel function, we obtain that this probability is less than, so the probability that z is less than 2.152 is 0.9843. So then the probability that z is greater than 2.152 is probability, 1 minus probability that z is less than 2.152, and that is 1 minus 0.9843. So this value is 0.0157. Okay? So this number is less than 0.05. So we reject the null hypothesis. Okay? So p-value is 0.0157. So that means this the event that our test statistic is greater than or equal to 2.152. The event that we have this t statistic, event that we obtain 2.152 as our t statistic, the probability that our t statistic is same as 2.152 is 1.57%. So this event would happen by chance about 1.57% if the null hypothesis is true. So if the null hypothesis is true, then our z statistic, the probability that we observe this z statistic is 1.57%. So it is very low percent. It is less than 5%. So that's why we reject the null hypothesis. And the p-value can be calculated by the Excel function, or we can calculate this p-value using appendix C2. So we have the p-value is 2.15, so 2.1, 0, 1, 2, 3, 4, 5. Then we have this number. So this number is probability that normal distribution is less than 2.15. So that is 0.984422. So the probability that z is greater than 2.15 is 1 minus probability that z is less than 2.15. So we have 0.0158 as the probability. So that is p-value method. Okay, so that is one example for the right tail test. Another example is the two-tailed test. Two-tailed test. We are testing the mean value, and population variance is known, or population variance is known, then population standard deviation is also given. So under this condition, we will do the two-tailed test. Two-tailed test is a little different from the right-tailed test or left-tailed test. So let's study it based on the example. The example is the same. We are doing the paper producing problem. So one company produced the laser printer letter papers, and we would like to check that this mean of paper width is 2.216 millimeter. And in the previous example, we suppose that we check that this width of this paper is greater than 216 or not, whether this width is greater than 216 or not. But in this example, we will assume that the null hypothesis is that mu is same as 2.216 millimeter. So that is two-tailed test. And the alternative hypothesis is that mu is not same as 216 millimeter. Okay. So the decision rule is different because our test is two-tailed test. So if our test statistic is between minus 1.96 and plus 1.96. So this minus 1.96 and plus 1.96 comes from the confidence level alpha. Significance level alpha is 5%. So our critical value is minus 1.96 to plus 1.96. If z statistic is between these two numbers, so it is located in here, then we do not reject the null hypothesis. But if our z statistic is located in this area, or located in this area, so left tail part and right tail part, then we reject this null hypothesis. And the left tail part starts at minus 1.96, and right tail part is started at plus 1.96. That is our decision rule. Okay, so we reject this null hypothesis if our z statistic is greater than 1.96, or if the z statistic is less than minus 1.96, then we reject this null hypothesis. Otherwise, we do not reject this null hypothesis. Okay. and this critical point is plus minus 1.96. So it is different from the right tail test. At right tail test, the critical value was 1.645, but in this case we have two-tailed test, so this critical value is a little different. Okay, because left tail and right tail should cover 2.5% and 2.5%. Okay, if it were right tail test, then we are concentrated on the right tail, and the right tail should be 5%, but we are doing the two-tailed test, so we divide this 5% to 2.5% left, 2.5% left, and 2.5% right. So that's why this critical value is changing. So be careful. You have to be careful to select this critical value. So when you select the critical value, you have to check that whether this test is two-tailed or right-tailed or left-tailed. Okay? And refer the table 2.9.2. Okay. Step 3. Calculate the test statistic. Calculate the test statistic. Test statistic is given by this equation, and our mean, sample mean, is 216.0070. I'm sorry, 216.00970, and our benchmark is 216 millimeter, and we know the standard deviation and the number of samples is 50, and we obtained the 2.152 as we studied in the previous example. And as you know, this 2.152 is again located in the rejection area. Okay, so here is 2.16. 2.152, I'm sorry, 2.152 is in this area, right tail area. So we reject the null hypothesis based on the two-tailed test. And the important thing is the significance level. At 5% significance level, we reject the null hypothesis, okay? Because our z statistic is located in the rejection area. Again, so then again we take the action. So we change the paper producing, the engineering and process, and we may change the machine to produce the paper or something like that. So again, we can use the p-value approach. So if the p-value is less than alpha, then we reject this null hypothesis. But in this case, we have two-tailed test, not one-tailed test. So p-value, calculating p-value is different. For the two-tailed test, p-value is 2 times, actually this precisely, p-value is probability that z is greater than absolute value of z calc plus probability that z is less than minus absolute value of z calc. So that is the p-value of two-tailed test, but as you know, this large z is a standard normal distributed random variable. But because the standard normal random variable is symmetric, and 0,1 is symmetric, so the positive tail and negative tail value is exactly same. So we just say that 2 times probability that z is greater than absolute value of z statistic. That is the equation for p-value of the two-tailed test. Okay? In this example, our t statistic was greater than 2.15. That is our z-calc. So in this textbook says that the z-calc is greater than 1.52, but we would better use large z instead of z-calc in here, and large z is normally distributed 0.1. So that is more precise notation, but whatever it is, you need not to be worried about this notation. Anyways, the probability that test statistic is greater than 2.152. So 2 times probability that test statistic is greater than 2.152 is our p-value, with this two-tailed test. So that was 0.0314. So that this says that two-tailed test result as extreme as 2.152 would rise about 3.14% of the time by chance alone if the null hypothesis were true. Okay? So this number is less than alpha, where alpha is 0.05, so that's why we reject this null hypothesis. But if you think that if you change the critical value alpha to 1%, okay, I'm sorry. So if you change this the significance level, if you change the significance level to 1%, instead of 5%, in this example we say that the significance level is 5%, but if you change this significance level to 1%, then this p-value does not reject the null hypothesis. Okay? The null hypothesis is not rejected because this number is greater than 1%. So if the alpha is 1%, then the null hypothesis is not rejected. Yeah? So the decision making is very much highly so depends on the level of significance. Okay. So this area is 0.157 and this area is 0.157. So p-value is again 0.0314. The final example is the testing the null hypothesis for mean with unknown population variance. Okay. So in this case, we have to use the t statistic. So let me discuss this problem again in the next video. Okay, I would better stop now. So it is enough. Thank you so much, and see you at next video. I will come with this testing mean with unknown population